is an extrinsic semiconductor or how we can define an extrinsic semiconductor. The semiconductors in which the impurities are added to the intrinsic semiconductor are called as extrinsic semiconductor. That means if we add some impurities to the intrinsic semiconductor, then those type of semiconductors are called as extrinsic semiconductor, and the process of adding impurities to the semiconductor is called as doping, and due to this doping the electrical conductivity of semiconductors gets increased. Hence the extrinsic semiconductors have higher electrical conductivity than the intrinsic semiconductor. Therefore, the number of electrons in the conduction band and number of holes in the valence band are always not equal in the case of extrinsic semiconductors. Next is types of impurities. There are two types of impurities that can be added to a semiconductor. They are pentavalent impurities and trivalent impurities. Now let us see the first one, that is pentavalent impurities. The pentavalent impurity atoms have 5 valence electrons in their outermost orbit, and the best examples for the pentavalent impurity are phosphorus, arsenic and antimony. If you see in this figure, this is the atomic structure for the phosphorus, in which the atomic number for the phosphorus is 15. So the number of protons and the number of electrons are same in the case of the phosphorus. So they are 15 electrons and 15 protons in the case of phosphorus. Now these 15 electrons are arranged in their orbits as 2 electrons in the first orbit, 8 electrons in the second orbit and 5 electrons in the outermost orbit. Now if you see here, the first orbit is filled with 2 electrons and the second orbit is filled with 8 electrons and the outermost orbit is filled with 5 electrons. That's why it is called as the pentavalent impurity atom. Next is trivalent impurities. The trivalent impurity atom has 3 valence electrons in their outermost orbit, and the best examples for the trivalent impurity are boron, gallium, indium and aluminium. Now if you see here, this is the atomic structure for the boron. The boron atom has 5 electrons and they are arranged in the shells as 2 electrons in the first orbit and 3 electrons in the outermost orbit. Now if you see in this figure, we can see that the first orbit is filled with 2 electrons and the second orbit, that is the outermost orbit, is filled with the 3 electrons. That's why it is called as a trivalent impurity atom. Next is classification of extrinsic semiconductors. The extrinsic semiconductors are basically classified into 2 types. The first one is the N-type extrinsic semiconductor, in which the number of electrons is greater than that of the number of protons, and the second is the P-type extrinsic semiconductor, in which the number of protons is greater than that of the number of electrons. Now if you see here, the letter N stands for negative, which are the electrons, and the letter P stands for positive, which are the protons. Next is N-type extrinsic semiconductor. When an pentavalent impurity is added to the intrinsic semiconductor or the pure form of semiconductor, then those type of semiconductors are called as N-type extrinsic semiconductor, and these pentavalent impurities such as phosphorus, arsenic, antimony are also called as donor impurities. Now if you see in this figure, the germanium is an intrinsic pure form of semiconductor in which there will be 4 valence electrons in the outermost orbit, and now it is doped with the arsenic atom, which is a pentavalent impurity atom, and it consists of 5 valence electrons in its outermost orbit. They are 1, 2, 3, 4 and 5. Now these 4 valence electrons in the germanium are covalently bonded with the 4 valence electrons in the arsenic, that is 1, 2, 3 and 4. Now these are the 4 covalent bonds which are formed between that of the germanium and the arsenic atoms. But 1 valence electron will be left free in the outermost orbit, and that is this one. This is the free electron which is in the outermost orbit of the arsenic atom. So this is how the N-type extrinsic semiconductor is doped into that of the intrinsic semiconductor. Next is conduction in N-type semiconductor. Now, when an external voltage is applied to the N-type semiconductor, then the free electrons moves towards the positive terminal of the applied voltage. Similarly, the holes moves towards the negative terminal of the applied voltage. That's why in N-type semiconductors, the electrons are the majority charge carriers and the holes are the minority charge carriers. Next is P-type extrinsic semiconductor. When the trivalent impurities are added to the intrinsic semiconductor or the pure form of semiconductor, then those type of semiconductors are called as the p-type extrinsic semiconductor, and these trivalent impurities such as boron, gallium, indium, aluminium are also called as the acceptor impurities. Now if you see here, the germanium is an intrinsic or the pure form of semiconductor in which there will be 4 electrons in its outermost orbit, and it is now doped with the gallium atom, which is the trivalent impurity atom, and it consists of 3 valence electrons in its outermost orbit, which are 1, 2, 3. Now these 3 valence electrons of the germanium are covalently bonded with the 3 valence electrons of the gallium, and those covalent bonds are 1, 2, and 3. And there will be an insufficient electron in the gallium to be bonded with the 4th valence electron in the germanium, and it is considered as a hole. If you see here, this is the insufficient electron to be bonded with that of the germanium, and so it is considered as the hole. So this is how the trivalent impurities are doped into the intrinsic semiconductor. Next is conduction in p-type semiconductor. As shown in the n-type semiconductor, it is similar way in the case of the p-type semiconductor. When an external voltage is applied to the p-type semiconductor, then the holes in the valence band moves towards the negative terminal of the applied voltage. Similarly, the free electrons moves towards the positive terminal of the applied voltage. Hence, in the case of the p-type semiconductors, we can say that holes are the majority charge carriers and the electrons are the minority charge carriers. Next is Fermi level in n-type semiconductor. In n-type semiconductor, the pentavalent impurities are added to the intrinsic form of semiconductor, and each pentavalent impurity donates a free electron, and the addition of pentavalent impurity creates a large number of free electrons in the conduction band. Due to this, the probability of occupation of energy levels by the electrons in the conduction band is greater than the probability of occupation of energy levels by the holes in the valence band. That's why the Fermi level in the n-type semiconductor lies close to that of the conduction band. Now if you see in this figure, this is the energy level diagram for the n-type semiconductor, in which this is the valence band and this is the conduction band, and this is the forbidden energy gap in which the Fermi level will be close to that of the conduction band. Next is the Fermi level for the n-type semiconductor is expressed as EF is equal to EC minus KBT log of NC by ND, where EF represents the Fermi level, EC represents the conduction band, KB represents the Boltzmann constant, T represents the absolute temperature, NC represents the effective density of states in the conduction band, and ND represents the concentration of donor atoms. Next is Fermi level in p-type semiconductors. In p-type semiconductors, the trivalent impurities are added to the intrinsic form of semiconductors, and each trivalent impurity creates a hole in the valence band and ready to accept an electron. The addition of these trivalent impurities creates a large number of holes in the valence band, and the probability of occupation of energy levels by the holes in the valence band is greater than the probability of occupation of energy levels by the electrons in the conduction band, and the Fermi level in the p-type semiconductor lies close to that of the valence. Now if you see in this figure, this is the energy band diagram for the p-type semiconductor, in which this is the valence band and this is the conduction band, and this is the band energy gap or the forbidden energy gap, and the Fermi level in the case of the trivalent impurities will be closer to that of the valence band. And the Fermi level for the p-type semiconductor is expressed as EF is equal to EV plus KBT into log of NV by NA, where EF represents the Fermi level, EC represents the conduction band, KB represents the Boltzmann constant, T represents the absolute temperature, NV represents the effective density of states in the valence band, and Na represents the concentration of acceptor atoms.